Hey everyone, back again for another deep dive, and this time we're looking at a paper that's really got people talking. Imagine you're trying to solve this crazy complicated puzzle, but instead of like moving pieces around, you're actually building an electric circuit.
It's definitely a wild idea, right? Using circuits to design optimization algorithms.
Totally. And I think most people are pretty familiar with the idea of optimization, at least in like a general sense. It's basically about finding the absolute best solution out of a whole bunch of options. So many things rely on optimization, like finding the best delivery route.
Or even something as complex as training an AI. That's where convex optimization comes in, and that's what this paper is all about.
Okay, so convex optimization. This paper is saying that there are some unexpected connections between that and electric circuits.
Exactly. So the authors noticed this really cool parallel between how electric circuits behave over time and how optimization algorithms work. It's like they both naturally try to find this like stable equilibrium state.
So they basically thought, hey, what if we use the principles of circuits to design totally new optimization algorithms?
Yeah. Specifically, they focused on RLC circuits, the ones with resistors, inductors, and capacitors.
Taking me back to physics class. But okay, so they're using these circuits as like a blueprint for algorithms. What does that even look like?
Well, the really cool part is they don't just stop at the analogy, they actually present a whole method for translating circuit designs into real working algorithms. And they even prove that these algorithms will actually converge to a solution.
Whoa, hold on. So we're not just talking about like theoretical similarities here. They've figured out a way to actually turn circuits into algorithms that can solve real problems.
Exactly. It's like unlocking a whole new way of thinking about and creating algorithms.
That's pretty mind-blowing. Okay, so what kind of potential do they see in this approach? What could this actually lead to?
I mean, it's potentially huge. Just imagine algorithms that are not only way more efficient, but also maybe even easier to understand and use. This could change a lot of things.
I'm definitely intrigued. Okay, so where did the researchers actually start with this whole idea?
They focused on two big innovations. First, they showed that a lot of the classic optimization algorithms, the ones that everyone uses all the time, can actually be seen as like discretized versions of electric circuits.
Okay, discretized, you're gonna have to explain that one.
Sure. So think about it like this. Electricity flowing through a circuit, it's all smooth and continuous, right? Discretization is kind of like taking that smooth flow and chopping it up into a series of steps.
Okay, so like turning that continuous flow into something more like a computer program that operates in steps.
Right. And their second innovation is something they call, and this is a mouthful, automatic discretization.
Catchy.
Yeah, well, what it means is they came up with a way to use computer software to basically take a circuit design and automatically turn it into a working algorithm. And they can even prove that it'll find a solution.
So they're not just saying, oh, hey, these things are kind of similar. They're giving us a way to actually build algorithms based on circuits.
Exactly. And that's what makes this research so powerful. It's bridging this gap between electrical circuits, which seem very physical, and optimization, which seems very abstract.
I'm starting to see why people are so excited about this. Okay, so they've got this foundation, this way of connecting circuits and algorithms. But do they actually show that it works? Like beyond just the theory?
Oh, yeah, they do. They took a bunch of familiar optimization algorithms like gradient descent, the proximal point method.
Right, those are pretty standard.
Yeah, and they actually show how you can build an electrical circuit that does the same thing as each of those algorithms.
So they're saying, hey, look, these algorithms we're already using, you could actually build a circuit that does the same thing.
Exactly. It's like seeing this unexpected connection between totally different fields.
All right, you've definitely piqued my curiosity. What's next? What else did they look into?
Well, next they bring in something called the Moreau envelope. Sounds a little intimidating, but it's actually pretty clever.
Okay, I'm all ears. Tell me about this Moreau envelope. What's it all about?
Imagine you're trying to optimize a function, but it's all bumpy and jagged. The Moreau envelope is like smoothing out all those rough spots, making it way easier to find the best solution.
So it's like paving the way for the algorithm to work more efficiently. I like it.
Exactly. And then they look at Nesterov acceleration, which is kind of like giving your algorithm a little speed boost.
Who doesn't want a faster algorithm? How does circuits play into that?
This is where it gets really interesting. They found that you can achieve Nesterov acceleration with a specific circuit design, and get this, it actually uses something called a negative resistor.
Wait, a negative resistor? Is that even a real thing? Doesn't that break the laws of physics or something?
It might sound a little crazy, but it totally makes sense in this context. In this particular situation, a negative resistor actually helps to stabilize the circuit and makes it find the solution faster.
So it's like a special kind of resistance that actually speeds things up.
You got it. It shows how creative they're getting with this whole approach, using these unusual components to get amazing results.
This is all very cool. So we've talked about how they represent individual algorithms as circuits. But what about when you have a whole bunch of algorithms working together? Like if you think about a swarm of robots or self-driving cars, they all need to coordinate their actions, right?
Yeah, that's where things get even more interesting. We call those decentralized algorithms.
Okay, I'm really curious to hear how they tackle that using circuits. That sounds like a whole other level of complexity.
It is, and that's actually a perfect place to pick up in part 2 of our deep dive.
Okay, so decentralized algorithms. How do circuits fit into that whole picture?
That's where this research gets really wild. So instead of having just one circuit representing a single algorithm, now you have a whole bunch of circuits like a network all connected together. Each circuit represents one of the agents in the system.
So going back to our swarm of robots example, each robot would have its own little circuit and it'd all be linked up somehow.
Yeah, exactly. And those connections between the circuits, like the wires, they represent the communication links between the robots.
I'm starting to visualize this. So the robots are like sharing information through those connections, just like electricity flowing through the wires. Okay, but what about all those circuit components, like the resistors and capacitors and stuff? How do those play into this whole decentralized thing?
Those are super important. They really capture all the little details of how decentralized algorithms work. Like, for example, you could have a resistor connecting two robots, and that resistance could represent how hard it is for them to communicate.
So a high resistance connection would mean the robots are having trouble sharing information, which could make it harder for them to work together effectively.
Exactly. And then you've got inductors, which can represent the momentum of each robot that helps them stay on course, even if they're getting conflicting information from their neighbors.
So even if one robot gets a signal that says turn left, but it's already moving to the right, the inductor helps it keep going until it can figure out what to do.
Right. It's like a built-in safeguard against overreacting to every little bit of information. And then you have capacitors, which can represent the robot's memory of what's happened before.
So each robot remembers what worked and what didn't in the past.
Exactly. That memory helps them make smarter decisions in the future, avoid making the same mistakes and all that.
This is pretty amazing. Like we're giving these robots a whole nervous system with memory, momentum, and the ability to talk to each other.
It's really cool. And the researchers don't just stop at the general idea. They actually go into detail about specific circuit designs for some well-known decentralized algorithms, things like decentralized ADMM and PG extra.
Okay, I'm going to be honest, those names don't mean a whole lot to me. Can you break those down a bit?
Sure. Basically, these are algorithms that are specifically designed for situations where you have information spread out across a network and communication is limited. Like decentralized ADMM, it's kind of like a really fancy negotiation protocol that lets all the robots agree on the best plan, even if they can't see the whole picture.
So they're all working together to solve the puzzle, even though they only have their own little piece of it.
Exactly. And then PG Extra builds on that by adding in some elements of prediction so the robots can anticipate what each other are going to do.
It's like they're developing a shared intuition, a sense of how the others will behave. That's really cool. But did they actually test these circuit designs out? Like in a real world setting?
They did. They actually did a practical experiment where they took a modified decentralized algorithm that was based on their circuit approach and they tested it against some of the standard algorithms.
Okay, I gotta know, how did it do?
It totally crushed the competition. Their algorithm was way better at solving the problem.
Wow. So this isn't just some theoretical curiosity. It actually leads to real performance improvements. I can definitely see why people are getting excited about this.
It's pretty groundbreaking stuff. And what's even cooler is that the researchers think this is just the beginning. They believe this approach can be used for so many different optimization problems.
Okay, now my mind is racing with possibilities. What kind of things could we use this for?
Well, we can dive into those exciting possibilities in the final part of our deep dive.
Okay, so we've seen how this whole circuit-based approach can change the way we design and understand optimization algorithms, even in those complex decentralized situations. But where does this all go? What can we actually do with this research?
The potential applications are huge, really exciting. We talk about robots and self-driving cars, but that's really just the start. Imagine using this for things like smart grids, where you have a whole network of energy producers and consumers that need to coordinate to, optimize energy distribution.
So instead of having these centralized control systems that can be, kind of fragile and inefficient, you could have a more decentralized system that's more resilient, where each part of the grid is making its own smart decisions based on what it knows locally and what it hears from its neighbors.
Exactly. That's just one example. We could also apply this to machine learning, where we're always trying to train algorithms to do these super complex tasks. Like imagine using these circuit-inspired algorithms to train a bunch of robots to learn from each other and adapt to new environments.
So it's kind of like taking that idea of swarm intelligence and pushing it even further. The robots aren't just following basic rules. They're actually learning and evolving their strategies together as a power.
Exactly. And one of the best things about this approach is that it's not limited to any specific hardware or software. The principles of circuits are, universal. So these algorithms could be implemented on anything from tiny little microcontrollers to giant cloud computing systems.
Like we found this universal language for optimization that can be used for any problem, no matter how big or small or what field it's in. The possibilities are really incredible when you think about it.
It really is a whole new way of thinking about optimization. We're moving away from seeing algorithms as just these abstract mathematical things, and instead we're realizing that we can get inspiration from the physical world to create solutions that are more intuitive, more efficient, and more adaptable.
It's this awesome combination of theory and practice, and I'm super excited to see where it all goes from here. It feels like we're just at the beginning of something really big in the world of optimization.
I definitely agree. And who knows, maybe there are other physical systems out there that could inspire new breakthroughs in algorithm design. It's a pretty fascinating area to explore.
Well, we'll definitely be keeping an eye on all of this research, and we'll be sure to share any exciting new developments with all of you. In the meantime, check out the show notes for links to the research paper and the researcher's website.
And if you're feeling inspired, maybe try playing around with some of the open source tools they've created. You might just be the one to make the next big discovery in optimization.
Happy optimizing, everyone.